but we haven't even got to the meat of it yet. The big reasons for color are interactions between, again, they're interactions between visible light and atoms or atomic sites, not just atoms. They can be atomic sites too. And we'll learn about things like color centers where you can get, instead of an anion, for example, you could have a space, a void that's filled with electrons instead of that anion to make up for the charge. So we're going to talk about crystal field transitions, molecular orbital transitions, and color centers. Those are the three big groups that we talk about in mineralogy when we talk about minerals and their color, their luster, and the varieties of ways in which light interacts with other properties of minerals like play of color, labradorescence, asterism, things like that. So opals, the way they look, things like that. That's play of color. So crystal field transitions have to do with the interaction between white light and partially filled d orbitals with chromophores. So this is where chromophores come in again. So we just talked about those transition elements, right? We talked about all of those transition elements that make up the chromophores that are happy color producing elements in various minerals. And they can be in trace amounts and they can be in the chemical formula itself. In fact, allochromatic means that the mineral receives its color from impurities or inclusions, or idiochromatic means the minerals actually contain the chromophores in their crystal lattice or in their formula. So again, allochromatic is just trace amount. So it's got like 0.1% maybe. Idiochromatic means that it's actually in the chemical formula, that the chromophore or that transition element is in the chemical formula. That doesn't really matter, but I wondered if somebody might ask about it, so I wanted to make sure that I understood the definition to explain it to you. All right, moving back to crystal field transitions, which is one of the three main topics that we're going to talk about. So again, this is with partially filled d orbitals. So the interaction between white light and partially filled d orbitals with chromophores, okay? These partially filled d orbitals will have lower or higher energy than the surrounding atoms with filled d orbitals. So the ones with filled d orbitals next to them or near them will have a different energy state than those with the partially filled ones. It'll either be higher or lower, but either way it'll be different. And those energy differences actually correspond to exact wavelengths in visible light. So interestingly, if this light is bright enough, this light would be bright enough, right? Basically just not dim light. And alexandrite is an example of why. I'll tell you why. So if you have decent light, and it's bright enough, it'll raise an electron from a lower energy d orbital to a higher energy d orbital. And it absorbs some of the light in that process. And then by doing so, because it's absorbing some of that visible spectrum, we see a color. This is very simplistic. If you're a chemist, there's a lot more chemistry. It's just that we don't really go into it unless this is specifically what you're going into for your PhD or something. Okay? I'm going over this very simplistically. So, olivine. Olivine is a green, maybe brownish green mineral. That's a very good example of this. In fact, I showed you some samples of olivine because the mantle is a lot composed of olivine. A lot. It's very green. So if red, again, the color red in the visible spectrum is absorbed, you're most likely going to see green. And that's what's happening in the case of olivine. And the energy required to actually raise an unpaired electron to a higher energy state is so much less than raising a paired electron. So that's why shining a light on it is enough. Make sense? Okay, this is a pretty basic diagram that is from one of the textbooks that I use, but it's modified from Loafer and Burns, 1976. And you can see that, just don't worry about the infrared. It does produce, this is other energy that is produced because of the process in which this happens, but this is all we can see, right? This is the area that we can see. So you're going to see that the red line, by the way, is garnet. It's a variety of garnet. So for a moment, just ignore the red squiggly line and only look at the green one. And that's representative of olivine. and its absorption of visible light. So you can imagine then that a lot of the violet is absorbed. I'm sorry. Yeah, that's right. And very, very little green and yellow is absorbed. So a lot of those other colors around the green are absorbed much, much more frequently or at much higher levels than the green is. So, of course, Olivine's going to appear green. Almondine Garnet, why do you think it would be red? Look at this line here. It's absorbing a lot of green. There's a little peak over the green. Very little yellow there, or a little bit of yellow there, and absolutely hardly any red. So that's the lowest absorption here is over the red. So you're going to see that Almondine Garnet is actually red, and it is indeed red. I have plenty of samples to show you. There's a lot of varieties of other garnet, like Sessertine and Grossular and Uvorovite, that can be a variety of other colors, but in general, Almondine Garnet is red. It's an idiochromatic element or mineral, so it would actually the chromophore is in its chemical formula, because that's how all the garnets are. All of the garnets change based on their chemical formulas in terms of their colors. You can get trace elements to change that up in addition to the main colors that they can be, but not always. There aren't always trace elements. Yeah, there's no numbers. It's really, for the scope of this, it's not that important, electron. I don't think. Yeah, I have some green garnet too, Pop Rocks. It's one of the varieties I have is Grossular, and the other one I have is Uvorovite. Yeah, but normally that would bother me, not having a number. But this has been measured, and there is a quantifiable, oh my gosh, yes, quantifiable number associated with it. So molecular orbital transition is due to the result between from the transfer of electrons between two adjacent cations. Cations are positively charged. These electrons that are transferred from each of these cations, they're delocalized, so they're not actually centered on a specific atom. So, for example, one of the best examples of this is Sapphire, where you've got electrons bouncing from titanium and iron and back and forth. So you get iron with a 2 charge and then titanium with a 4 charge, and it switches to iron 3 and titanium 3. And that goes back and forth and back and forth and back and forth. And what happens with that is you get a release of visible light. It's actually absorbed as energy, right? And that yields blue to our eyes based on the spectrum, which I will show you now. So due to molecular orbital transition, you see the blue in Sapphire. Here's another thing though. So you see the blue in Sapphire because of molecular orbital transitions, but you see the red in Ruby because of crystal field transitions. So did you guys know that corundum produces your sapphires and your rubies? It's the same mineral. It's an aluminum oxide. So if one thing happens, right, if you've got the crystal field transition happening, yeah, corundum is really cool. So you get red because of one type of chemistry, and you get blue because of a different type. So you get, again, the transference between delocalized electrons produces the blue in Sapphire, and the unfilled d orbitals and the differences between their charge of adjacent atoms causes the red in Ruby. So they're the same element, but based on the chromoforms that are there, can produce a completely different type of chemistry, which results in what we see, either red or blue. How cool is that? I think that's so cool. So again, the red is produced because of the unfilled d orbitals that have differences in energy next to different atoms. And those differences in energy produce the red in a ruby, which is a crystal field transition, or the molecular orbital transition, where you've got delocalized electrons that transfer from one another, like the iron and the titanium, that can also be in trace amounts in corundum, that produces the blue in Sapphire. I think this is so cool. But this is just another diagram that we saw. Again, yes, there are no numbers on the y-axis, but for the sake of this lecture, it's fine. I'm just showing you the general representation of actually what this wavelength looks like in blue sapphire, what the wavelength looks like in terms of absorption. So you see that very little blue is absorbed. Well, surprise, Sapphire's blue. Now, finally, on to color centers. This is the last topic of the night, and then I'm going to talk about play of color, chatoyancy, labradorescence, asterism, and fluorescence tomorrow. Okay? It'll be probably pretty short. All right, so color centers are just defects, essentially, in a crystal structure where there are vacancies, where electrons, excess electrons, can actually fill instead of the missing ion. Fluorite. This is the case of fluorite. Very, very, very popular mineral. And in the case of purple fluorite, this is why we see purple in fluorite, is because of color defects and the vacancies that are filled by excess electrons. And in this case, the ion that's missing is the fluorine anion. Anions have a negative charge. So the fluorine anion is either it's missing for a variety of reasons. It's either caused because of, in this case, an excess of calcium in solution, such that it's an abundance, not enough fluorine, and you're going to end up with some vacancies where the fluorine should be. Or radiation of the mineral can happen and boot some of those fluorine anions out of the crystal lattice. And then you might get, of course, that charge is going to need to be balanced, so you're going to get the excess of electrons filling that vacancy to neutralize that charge. So I have a little example for you there. So this is what would be a normal crystal lattice of a fluorine, two-dimensional fluorine crystal lattice. Okay, you're not looking at the three-dimensional structure. You're only looking at essentially a cross-section. So you've got your big fluorine anions, and the anions are always bigger. They can be a 1-to-1 ratio. So you see that in A, you have no missing anions or cations. The cations here are the calcium. The anions are the fluorine. Here, maybe this was irradiated. Maybe it was, there's too much calcium in the system such that just isn't enough fluorine to bond quickly with the calcium ions in the solution. So you end up with some excess electrons filling that vacancy to neutralize that charge. I like it. It's pretty simple, but it's good.